Hello, everyone, and thank you for joining the session today. My name is Alex Goldblatt. I am a product manager for the Oracle Backup and Recovery Services. With me today, presenting Andrew Bob, MA Solution Architect. Andrew, would you introduce yourself?
Yes, hi. As I say, my name's Andrew Babb. I work in the database development group and specifically the MAA solution group.
Thank you, Andrew. So today's session is going to be dedicated to the overview of the deduplication technology, and we're also going to be discussing different approaches and Oracle approach to the deduplication solution overall. And the reason why we decided to do like a historical dive, if you would, into where the deduplication, how it was originated, what was the goal, how technology evolved, and what do we have today. We decided to have this discussion just to ensure that you guys have complete view of the backgrounds, and it's actually going to help to the overall conversation going forward. And what we're going to do, we will basically just start from the very beginning, where this technology came from and how this technology actually just started. And to me, the beginning of the overall venue of the deduplication technology development started with the acquisition of the Belgium startup company by EMC back then, and creating a so-called content addressable storage market. Why it is important? It is important because it brought up a number of technologies, and all of them are fundamental today, dealing not just with the deduplication technology, but also with the basic constructs, like, for example, origination of the REST APIs, the public APIs, the storage that actually is not running on the fiber channel connectivity, but actually running on the IP rather than anything else. We also see introduction of the so-called hash algorithm at this point. Why it is so important? It was basically just a side effect of the content addressable storage development, but it played significant role. When MD5 hash was introduced as the mean to access the actual object, that actually created also a question, okay, so if I have a hash and it is associated with a specific object in the file system, how can I ensure that this object is actually unique in the system and there are going to be no two identical objects generating the same hash? To make things worse, in 2005, on one of the worldwide conferences, one of the famous mathematicians actually introduced a model breaking the myth that MD5 hash is actually generating unique fingerprints. So he actually created some multitudes of the non-identical objects creating the same fingerprint. So that's almost puts content addressable storage in havoc, and development had to be extremely creative to introduce additional prevention ways of how to ensure that objects are not going to be generating the same hash, and so there are going to be no collisions in the system. So they came up with the concept of the collision prevention. So, for example, EMC, they decided to add one byte at the end of the object if it was generating identical MD5 to ensure that it's going to be absolutely unique and in the global system. So later, to enhance the security of the MD5, we can see actually a combination of variety of additional hash calculations on the top of MD5, such as SHA-2, 256, etc., etc. So again, the notion of the fingerprints and its origination basically came by the way of the desire to manage unstructured data. So essentially, the storage was thought as the archiving, meaning that you have to provide with infinite capacity and infinite retention management for the massive scale of the storage of the unstructured data in the system. Okay, so you have an object, you do 128 to 256 digital fingerprints, you send it back to the application, And this is how application can access data in the actual system. And so this is just exactly what you see right here. Okay, so on the left side, you have a definition of the blob, binary large object, which also kind of originating terminology from that's content addressable storage. And then you have storage which is based on the XML formats and descriptive metadata in the system itself. The XML, that was another breakthrough. And so this is just a unique way of the creating what today known as metadata tags. Why it is important? Because you can, at this point, associate not just the, say, I have an image, MRI image of XYZ, but actually this MRI image belongs to Alex Goldblatt, and so it was done by the provider XYZ, and it should be stored for 7 years. So all this bulk of the metadata and association with the actual physical object in the system, plus MD5-based access to this object, was a crucial development to a lot of technologies that today we basically perceive as a complete commodity. So that was basically fundamentals of the deduplication. And now when you're going to take a look at the kind of basic of the deduplication technology overall, you can easily see the resemblance. Okay, and so first and foremost, you have the same fingerprinting technology as the fundamentals of the deduplication overall, right? And then the difference between the CAS, so the content addressable storage, and Dedupe today is that deduplication storage took it one level down, meaning that they decided to optimize not just on the object level or the file level, but also to optimize it on the sub-file level, meaning breaking down into the segments and to figure out what is changing and what is not. I can give you just a couple of examples. The best systems known for the deduplication efficiency are Exchange, for example. Why it is working so nicely? It works so nicely because all the net new data in the backup system for Exchange actually appended at the tail. So you effectively, on the daily backup, so you can easily see efficiency of like 99%. The same applies to the file system. Not necessarily applicable to a lot of applications. So there are different data types that can be deduped easily and that cannot be deduped easily. And that basically led to two fundamental differences in the approach to the dedupe on the subfile level. As you can see, one is called fixed block, another one is called variable block. Fixed block was basically commodity dedupe that was invented first, and then Quantum came up with a variable length segmentation. So what is the fundamental difference between the two? One is basically just take the file and chop it in predictable chunks. And typically, it's 2 to 4K chunks that's being stored in the system. The problem is if you have a file that actually changes, not at the tail, but somewhere in the middle, but leaves intact the rest of, the fixed block will fail to identify this change and most likely will generate a lot of new chunks, even though that it could be deduped in a more efficient manner. So that's the essence of the Quantum. Quantum developed algorithm that allows not just to chop to 4K chunks, but also to run the stream analysis to identify if boundaries of the chunks are actually shifted. So obviously efficiency is much higher for the specific data types, not for all. Like for example, for Exchange, both algorithms are going to be just fine. But for some other streams, it might not necessarily hold true. The efficiency of the variable length segmentation actually leads to the higher usage of CPU, which is pretty much obvious because you still have to do the analysis and to build to the bitmap before you're going to be identifying what can be deduped. And that actually led to a lot of commonly seen technologies beyond just backup images, like for example, optimization for the disaster recovery, meaning I do not have to send that much data for the replication, cross-site replication, and it led to practically overhaul of the multi-site disaster recovery practices. So just to explain like a little bit more in depth, okay, so this is where it all started, okay, so this is just the fundamentals of the fixed block deduplication. So you have contents, you have basically just backup stream, you run the MD5 or SHA-12 or 256, you identify if the object is unique in the system, then you break it down, you send the object to the metadata server, meaning you create fingerprint number 1 for the object itself, and you send chunks that also are being fingerprinted and stored in the system, but on the storage device at this point. Then you have the second object, and so obviously it has identical fingerprints. Therefore, it's not unique in the system. You don't have to back it up. You just create the pointer to the old object from the new one, saying that if you're going to need to recover it, it's going to be identical, but you're going to save 100% of storage. And then the last one, it's not identical, but when you break it down into the chunks and you create another fingerprints in the metadata device, you send only 2 blocks to the storage system, saying this is going to be mapped against the second fingerprint, and therefore you can restore it easily. Now, it would be really nice and rosy, but it doesn't work this way. In reality, back then, when it all started with just a basic fingerprinting, development kind of failed to realize what kind of complexity in the massive scale it's actually going to take. And the original desire to basically compete with LTO2 tapes on both performance and scale rapidly evolved into much bigger conversation. And first problem that appeared was actually restore speeds, not even backup speeds. So the problem was that if you take a backup and then you delete some backups from the system, it creates gaps. So the file system rapidly evolves into the defragment its capacity with non-linear reads, if necessary, to recover an object. Because you have to locate to this object in file system, and it takes time, and it takes to go from the one line to another line, and it just pop up the variety of blocks to rehydrate the object itself to restore. So that led to a lot of really complex background processes that actually addressed a lot of gaps of this kind. So one was introduction of the containers versus just blocks to ensure that you're going to have locality and you have a chance to have a linear read. So another one is a garbage collection that was primarily introduced by data domain system because data domain fundamentally doesn't do inline deduplication. Actually, you send backup data, and then they run garbage collection at the designated errors, and that actually does the deduplication because it basically just compares the new chunks and the old chunks in the file system. The same applies to additional perks because people realize that when you have complicated system that not just the file system, but also the indexing, the mapping of the object's fingerprints versus chunks, it might be prone because of the underlying storage failures, because of the variety of systems. So that actually just led to additional development of the damage prevention and the security of the overall storage system at this point. And so this is a typical example. This is Dell data domain, the PowerProtect data domain system that has this type of the data integrity and vulnerability prevention architecture embedded in them. I'm not going to go over the slides, but that just shows how complicated it is. And this is not even scratching the surface of how complicated this development was to ensure that the system and data are going to be sustainable, irrespective to how long you have to retain your data on the system itself. And then it came to realization that if you just have the backend deduplication, it's just not good enough. Why? Because it doesn't address one problem. You still have to send 100% of the backup data to the secondary storage, and then it's got to be deduplicated. So vendors like Veritas, vendors like Dell EMC came up with the enhancement for the client deduplication. So in the case of the EMC, that's MMR platform, and that was the originator of the client deduplication. In the case of the Veritas Net Backup, that was a pure disk client infrastructure that was integrated with Net Backup at some point. So if you're going to take a look at the data domain boost, as you can see, it's basically on the backend. So if you send just pure data, you have to ID the segments. So you have to ask the question if it is unique in the system. You have to compress, and then you have to write into the file system, right? So they basically uploaded segment identification and compression to the client, and therefore achieving two major goals. Number one, to basically optimize the overall network utilization between the client system and the backend. But more importantly, also to offloading processing speeds and feeds, distributing between the secondary storage and the client. So it does impose overhead on the clients automatically. There is no any other way to distribute the overall workloads, right? So whether you like it or not, so if you install data domain client, for example, for Oracle, on the Oracle system, when it's going to be taking backups, it's going to run deduplication, it's going to run segmentation, it's going to run compression before sending data over. Yes, it will create an overhead. Nevertheless, backups obviously run faster because you basically do pre-processing on the client side, and you lower CPU utilization on the backend, as you can see, 20 to 40%, right? Is it worth it? Well, the answer is yes, but not necessarily for all the circumstances, because if you have business critical application and you pack your CPU on the client system, it's probably not the best way to back up things. So what else was invented? Virtual synthetics and incremental forever strategy. Incremental forever strategy was invented by IBM, and it was a Tivoli backup manager. The problem with Tivoli backup manager was it created the strategy of the incremental forever, but it was running on the physical tape. So to recover your system, oftentimes you had to mount 10, 20 tapes just to find your incremental, so to restore the system. It was slow, it was sloppy, it was error prone. So when deduplication technology came along, the notion of the incremental forever actually started making sense, because you send only unique chunks in the system. The second part of the invention belongs to data domain, was introduction of the virtual synthetics, meaning that if you take the incremental backup, and if you can map it against the old chunks already existing in the system, you can create a point-in-time backup image at any given time and introduce it back to the system to restore it as a full image instead of the running base and incremental recovery and incremental recovery, et cetera, et cetera. So that was a huge breakthrough. The only thing that I have to mention, it doesn't work on all data types. So the problem is when you cannot identify or cannot identify in the system uniqueness of the chunks. For example, if data are encrypted or compressed by the client system, you have to generate net new whole image all the time. And it belongs to a lot of data types. Okay, so outside of the file system, outside of the usual suspects like the same exchanges or SQL servers, if you run, for example, TDD encryption for Oracle database, it's not going to work. And we're going to talk about it in just a second. But the concept and the introduction of the incremental forever strategy was absolutely crucial to the data protection industry overall. And with that, I'm going to defer to Andrew to explain why deduplication is not a complete answer specifically for Oracle databases. Andrew, please.
Thanks, Alex. So if deduplication is not the answer, then what is? Sorry, next slide, Alex, please. So with the introduction of the zero data loss recovery appliance, Oracle has introduced the concept of incremental forever architecture. After we perform an initial full backup, incremental level 1 backups are performed on a daily basis. And these backups are then converted into virtual full backups by the recovery appliance. The use of incremental backups reduces backup overhead and network utilization by 10x, as well as providing significant space saving on the recovery appliance. This allows for long backup histories to be kept on the appliance using the smallest possible space. In fact, if additional level 0 backups are sent into the recovery appliance, then those backups will be deduplicated by the appliance, removing any identical blocks. Next slide. So how does Oracle achieve this? So the Oracle database has the block change tracking feature, BCT for short, which tracks which blocks have been changed between incremental backups, similar to an index in a book. RMAN uses the block change tracking feature to read only those blocks that have changed, thereby reducing the amount of data needing to be read and the amount of data needing to be sent to the appliance. As mentioned previously, other deduplication products require the entire file to be read in order to achieve the high storage savings. Next slide. So if we look a little deeper at the block change tracking feature, the BCT feature is implemented as a special file within the database with 1 bit representing 4 Oracle 8K blocks in a data file. If any one of those 4 blocks changes, then the bit is flipped automatically by the Oracle database. RMAN, when it runs, will then read the BCT file to identify which blocks might have changed, and then send the changed blocks to the recovery appliance. If you're running on an Exadata engineered system, this filtering is pushed down to the storage cells further, reducing data transfer between tiers. That's using the Exadata Cell Smart Incremental Backup feature. So if we look at the numbers, if we have a 10 terabyte database with a 2% change rate, then Oracle, and specifically RMAN, will read just 200 gigabytes from disk and send 200 gigabytes to the backup destination with the use of the BCT feature. Other deduplication products will need to read and send the entire 10 terabytes of data to the deduplication device. Next slide. So Alex touched on this. What do we do with encrypted data? Typically, encrypted data does not compress very well. It's similar to zipping a zip file. The ultimate file may actually increase in size. New with the Oracle Database Autonomous Recovery Service available in the Oracle Cloud, OCI database backups can now compress encrypted data. The data is read by the protected database and then decrypted, compressed, and then re-encrypted, all on the database host. And the resulting encrypted data is sent to the recovery appliance. The recovery appliance does not have access to, nor needs access to the encryption keys. And in fact, the encryption wallet cannot be stored on the recovery appliance. This is a best practice to keep the wallet and the data separate. By allowing the encrypted data to be compressed, we're seeing a 2x saving on the recovery service compared to the traditional backing up of encrypted data. And once again, the recovery service does not have access to the keys. The data is stored securely in the recovery service in an encrypted state, and the database servers handle the encryption and decryption locally. Thank you. Next slide, Alex.
Thanks, Andrew. So let me just kind of summarize what we just discussed. Okay, so there are a lot of differences between the technologies, the traditional technologies of data domains and quantums and cohesities and rubrics and what we do within Oracle. The major differences that Andrew just explained is that two things. One, we own Oracle database. So basically our technology is heavily embedded in the core of the actual database. And that allows us to have this unique approach. And this is why we can even deal with the TDE encrypted data, just because we have access to the origination of the data stream itself. But if you're going to take a look at the kind of scratching all the deficiencies, pros and cons between the backup vendors and Oracle, it comes down to two things. One is BCT, and Andrew just alluded to this fact, is not deduplication. For the guys that's basically just more like entrenched into the traditional backup system, you can compare it to the VMware change block tracking, which everybody's using. So basically, we do exactly the same. We identify what actually is changing in the core of the database, and we can actually do this on the transactional level without even hitting the spinning disk again. So we just basically just deal with the memory buffers to identify what actually changed in the database and send instantaneously on the transactional level data to the recovery system. The essence of the virtual backups that we create, and this is also unique to Oracle because nobody else can actually create instantaneously point-in-time virtual synthetics. They have to run RMAN heavy operations just to generate the virtual synthetic, and it's still not going to be on the transactional level. But unlike everybody else, we do this just again because we know how to map changes identified by BCT versus original L0 backup that we took at some point of time. And that allows us to introduce a faster recovery because we do not need to apply L1 to the L0. We create point-in-time image, and we can send it back to the original or to the alternative destination instantaneously. So things implemented today within the OCI Oracle Cloud recovery service, as well as on-premises ZDL array, the recovery appliance, are pretty much have parity between, and they allow to provide much more efficient way to deal not just with the backup practice, but also with the restore. Now, what is the difference between us and the other guys is they have general purpose, right? So the algorithm that I explained earlier, the fixed block, the battery block, or the combination of both, they basically apply because they have to deal with a variety of the input data for backup applications that we don't have to do. We do not deal with the VMware today. We don't deal with any other data types outside of the Oracle database for the variety of reasons. Pretty evident why. But they have to deal with it. So they can deal with different data types, but at the same time, when it comes down to the Oracle system, because of the limitations of the RMAN backups and because of the limitations of the typical approach when you have to take weekly L0s and then you have to take L1s every day, plus archive lock sweep, has its own deficiencies in a sense of the performance and complexity of the restore. On the top of everything else, one of the things that's kind of outside of the deduplication, but worth mentioning, is the typical verification of the quality of backup system that we also run instantaneously on the recovery appliance or recovery service itself. Therefore, you don't need to spend that much cycles, and we do not overload client system by much. So again, if you will defer to typical client deduplication like data domain RMAN clients, because we know how to deal with it, and we send only changes to the backup system, we just simply do not abuse client system because we don't need to really distribute much of the processing from the recovery appliance to the client and to PAC CPU on the production system itself. This slide, we have a lot of resources. Please get familiar with that. So we have a lot of collateral that might be extremely useful for you guys. We also have product demos for the backup monitoring and restore. And also please get familiar with the Oracle Autonomous Recovery Service in the cloud. I think it would be extremely beneficial to you guys running your database services within Oracle. And with that, let's take a look at Q&A. Don't general purpose backup vendors also use RMAN to backup databases? Would they benefit from BCT as well? Or am I missing something? Yes, Anders, it is an absolutely valid question. Indeed, it would be beneficial to everyone, but unfortunately, we live in the competitive world. And even though that's on the surface, it would be beneficial for everyone to open it up like VMware, change block tracking. Because there is a strong dependency on the not just RMAN client, but also on the database itself, as I mentioned, it brings just extremely complicated matter. Okay, so if doing something like that, we would have to certify all the partners in the world and to run the hardware compatibility metrics and to do a lot of really difficult stuff that we do not want today to deal with. Because already RMAN client, standard client is available for everybody, people kind of learned how to deal with these type of the situations. I think it would be fair enough for us to ensure that you as customers will be benefiting from the technology, from the overall technology that Oracle provides. So like, for example, the same OCI cloud service. We cannot open cloud service for everybody. It's just impossible to do, right? Because it's predicated on the variety of factors, including integrated solution between the EXA database dedicated or EXA, the base DB service or the autonomous DB services and the recovery service. And it's absolutely impossible to maintain this type of the integration cohesiveness if you will somehow open it up. It's not going to be fairly well for you as a customer base, and also for us as the software providers. Do we have any other questions? How does ESBT decrypt compression encrypt resource consumption compared to data domain boost resource consumption? Excellent question. Andrew, would you like to take this one?
Actually, Marco responded to that with the performance evaluation, we haven't completed the performance evaluation against DD Boost, but the utilization that we're seeing with encrypting SBT is relatively low. And by that, we're talking a couple of percentage points is what we've seen when we've been doing our testing with encrypting SBT versus the non-encrypting SBT. I don't have access to the DD Boost though, so that would have to be done as a competitive analysis.
Yeah, one of the things that worth mentioning, there is no really publicly available performance metrics for data domain boost to start with, especially on the restore side. So the only thing that EMC is publishing is how much of the network savings it can bring you, right? So we've seen different numbers, like in the case of the actual implementations, when because typically you have a combination of different vendors. Like, for example, people buy recovery appliance, but at the same time they run EMC networker or the Power Protector Manager just to cover the rest of the enterprise. So sometimes it just gets to the point when people believe in the efficiency of the Oracle integrated solution with recovery appliance or with the recovery service, because other vendors fail to deliver the efficiency of the recovery and sometimes efficiency of the actual backup. I can give you just one example. One of the large financial institutions that have massive half petabytes database, so that cannot be backed up by anyone else but by Oracle. Because of the massive size of this database. And basically what we do with the recovery appliance, We not exactly backing up. We, as Andrew mentioned, with the change block tracking on our side, we practically create instant clone of the database on our system. That allows you to provide with the extensive set of the features that actually just creating this paradigm when we can deal with a huge amount of data and at the same time not to overload the client system just because of the unique way of what we do in the backends, but also what we do on the client system, just again, because of the integrated solution with the Oracle database itself. And I don't see any other questions. So I guess with that, thank you so much for joining the session. I really appreciate your time. Have a great weekend.